So we started this topic last Wednesday, hydrodynamics. So hydrodynamics is the study of fluid in motion. We mentioned the assumption of an ideal fluid, which are non-viscous, incompressible, and non-turbulent. We also stated the types of fluid flow, which are basically two at your level, laminar flow and turbulent flow. Then how to determine if the flow is laminar or turbulent. So by that, we use the Reynolds number to determine the flow, and we discuss flow rate, what a flow rate is, that is the volume of fluid flowing across a given area at a given time. Q is equal to V over T, which is also written as AV. AV, that's A for area, V for velocity. Then we derive the continuity equation as A1 V1 and A2 V2. A for area, V for velocity. And then the mass flow rate as rho AV. And then we went on to Bernoulli's principle, which gave us relationship between velocity and pressure. So velocity and pressure are inversely proportional. As the velocity of a fluid increases, the pressure decreases. And we have the expression for Bernoulli's principle as P1 or P plus half rho V square plus rho GY. So if we are looking at a system such as we have in that figure, where we have the pipe elevated above the ground, and then the fluid is entering at a particular part and coming out at the other part. The expression becomes P1 plus half rho V1 square plus rho GY, which is equal to P2 plus half rho V2 square plus rho GY2. And then we stated the Bernoulli's principle as for a streamline flow, the sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume remains constant. That is the statement of the Bernoulli's principle, which is translated to the formula: pressure, kinetic energy per unit volume, and gravitational potential energy per unit volume remains constant. Then we applied Bernoulli's principle to Venturi tube. By Venturi tube, a pipe that is laid horizontally. So since the pipe is laid horizontally, it implies that there is no elevation. So the height parameter Y1 and Y2 are at the same level, which implies that they become zero. So in Venturi tube, applying the Bernoulli's expression, the height parameter section is zero. So that is why the equation has been transformed to P1 plus half rho V1 square is equal to P2 plus half rho V2 square. Now, it could be asked to determine the speed at which the fluid is flowing in or flowing out. So let's assume that you don't know the speed at which the fluid is entering a pipe, but you are asked to find the speed at which the fluid is flowing out at the other end. We can combine the Venturi tube equation and then the continuity equation to solve for that. So if we eliminate V1 in Venturi tube, eliminate V1 in continuity equation and write V1 in terms of V2 and substitute that That is V1 is equal to A1 over A2 times V2. Substitute that expression in equation 2 into equation 1, where we have P1 plus half rho V1 square. So where we have V1 square, you replace it with A2 over A1 V2. So when we do that and simplify the expression to make V2 the subject of the formula, we are going to have V2 is equal to A1 square root 2 P1 minus P2 over rho A1 square minus A2 square. So that will be the expression, and that you can use that to find the speed at which the fluid is flowing out from a pipe. Now, we can also apply Venturi Bernoulli's principle to a system or a tank containing a fluid, or liquid, and then there is a small hole. The small hole is not visible for you to see, but you just notice that fluid is leaking somewhere, but it's not conspicuous. You can't see where it is actually leaking. And because normally, if you have a container that has, let's say, water inside, and somewhere by the base, by the bottom, fluid is leaking out, you will see the water level, the height of the water level decreasing as the fluid is leaking out. But this time, the water level, by what we are trying to discuss here, the water level dropping is not visible, it's not known, but you just notice that there is fluid or water leaking somewhere. Where it is leaking is not visible, and the level of decrease of the height of the water in that container is not conspicuous. So in that case, how do we find our speed at which the water is flowing out of that small hole? So that brings us to Torricelli's law. So Torricelli's law also considered to be a speed of efflux, gave us that insight of what is actually happening to a system like that. So the speed V, the speed at which the water will be flowing out of that hole is equal to V1 is equal to square root of 2 P minus P atmosphere over rho plus 2GH. The derivation is there. But what you need is that expression. Now, if you look at that figure, you will see that the tank is covered. The only place that is exposed to the atmosphere is the side where the fluid is leaking. So at the top, there is pressure. At the side where the fluid is leaking, there is pressure. So at the top, the pressure is P. At the side where the fluid is leaking, the pressure is atmospheric pressure. Then the fluid has a uniform density. So we are applying Bernoulli's expression. We have that expression that you see, V1 is equal to 2 square root of 2P. The P is the topmost pressure, and the P atmosphere is the pressure by the side of the tank where the fluid is leaking, all over density plus 2GH. Now, if we decide to open up the container so that the tank is, the top of the tank is exposed to the atmosphere. So if we open up the container and the top is exposed to the atmosphere, it implies that the pressure at the top becomes atmospheric pressure as well. So in that case, we have the top of the tank open to the atmosphere. We have the side where the fluid is leaking open to the atmosphere. So we have two atmospheric pressure operating in that system. So our P minus atmospheric pressure becomes P atmospheric pressure minus P atmospheric pressure. So since they are the same, that will give us 0 in that term. So our equation becomes V is equal to 2GH. V becomes 2GH. Now, this formula is a formula of a free falling body through vertical height. Free falling body through vertical height. In your equation of motion where you have V square is equal to U square plus 2AS. V square is equal to U square plus 2AS. If an object is falling from a height, remember that A becomes acceleration due to gravity. And since the object is falling from the height, G is positive. So our equation becomes V square is equal to U square plus 2GH plus 2GH. Now, when an object is falling freely from a top, let's assume that an object was dropped from a top and is falling. Remember that there will be no initial velocity, which implies that in that equation of motion where we have V square is equal to U square plus 2GH. The U square becomes 0 because the object is falling freely from the top and there's no initial velocity given to it. So that expression becomes V square is equal to 2GH. To find V becomes V is equal to square root of 2GH. So if you look at the expression we got for applying Bernoulli's equation to Torricelli's speed of efflux, the equations are the same. So if the tank is open to atmosphere, the speed of efflux for an open tank is equal to the speed acquired by a free falling body through a vertical height. So the law eventually states that the speed of efflux of a fluid through a sharp edge hole at the bottom of a tank filled to a depth h is the same as the speed that a body would acquire in falling freely from the height h. And that is given as V is equal to square root of 2GH, where G is acceleration due to gravity, 9.81 meter per second square, and H is the height of the tank. The next is Poiseuille's law. Consider a fluid of viscosity moving through a cylindrical pipe of length L and internal radius R under the influence of pressure difference. The average flow rate, according to Poiseuille's law, is equal to pi R4 change in pressure over 8 nor L, nor for viscosity and L for the length of the pipe. So change in P there is the pressure difference from the entering to the exit, while R is the radius of the pipe, then L for the length of the pipe. Now we move on to terminal velocity and Stokes' law. Experiments have shown that when a small object, such as a steel ball bearing is dropped into a viscous liquid like glycerin, it accelerates at first, but its velocity soon reaches a steady value known as the terminal velocity. At this point, the viscous force or the drag force and the buoyant force upthrust of the liquid on the object acting upwards are together equal to the object's weight acting downwards. So here we have a solid ball that is dropped in a viscous fluid. So just picture a small metallic ball dropped in, let's say, honey or palm oil. Now, remember that whenever an object is falling through a liquid or a fluid, there is a restraining force. There is upthrust. That is the force that is stopping the object from falling down freely. So that is the viscous drag force. Then this object itself will have a weight force that is exerting on the fluid to go down. So that is the weight of the object. And then the fluid itself will be resisting the object from going down. So we have three forces: the viscous force, then the buoyancy. The viscous force, that is the drag force, and then the buoyancy as well as the weight. The weight is going down, the viscous force is going up, the buoyant force is also going up. Now, at a point, initially when the object is dropped, it will be accelerating. But at a point, the speed becomes constant. Remember, when speed is constant, acceleration becomes zero. When speed is constant, acceleration becomes zero. So now when the speed becomes constant and acceleration becomes zero, the speed at which the object is moving through the fluid is called the terminal velocity. Terminal velocity. So we have three forces that are operating on this object as it's going down. By applying those conditions that the object is at a terminal velocity, drag force restraining the object from going down, buoyant force restraining the object from going down freely, and then the weight of the object pushing itself downward. If we consider these conditions, we can derive an expression for the terminal velocity. Mind you, the drag force is also called Stokes force. The drag force is also called Stokes force and is given as F is equal to K nor RV. K nor RV. K, where K is 6 pi. Where K is 6 pi. So if we substitute the value of K, that becomes F is equal to 6 pi nor RV. So that is Stokes' law. Now, back to terminal velocity. To derive the expression for the terminal velocity, we have three forces. One is going down, and two forces are going up. But they are balanced because the speed is constant. So since the speed is constant, the two forces are balanced by the weight force. So if we write an expression for that, we have this F is equal to W minus U. F is the drag force, and then W is the weight of the object going down, and then U is the upthrust. U is the upthrust. So to simplify that, you will see what I have done there. Weight is equal to mg. So that is mass times acceleration due to gravity. And if you recall, on Wednesday, we converted our mass to density volume. So our weight becomes density, volume, and acceleration due to gravity. But this time, our volume, since the object is a sphere, our volume of the sphere becomes 4 over pi r cubed. 4 over pi r cubed. So if we substitute that into the weight formula, where we have mg is equal to rho vg. So we are going to have 4 pi r cubed over 4 rho g. Rho g. So we are going to have this expression there. Now remember upthrust. Upthrust is equal to weight of the fluid displaced. Again, weight of the fluid displaced is the same as weight of the volume of the liquid. This mgh again comes in there. But this time, remember, the first one we are talking of the weight of the sphere. So the density there is going to be the density of the spherical ball. While the upthrust, which is as a result of the fluid resistance, so the fluid resistance, at that point, our density will be the density of the fluid. So we are still going to have this expression 4 pi r cubed, density of the liquid, and acceleration due to gravity. So we have that. Now, the force there is drag force, which is the viscous force given to us as 6 pi nor rv. 6 pi nor rv. So if we substitute all these three expressions, 1, 2, and then 3, into this equation, and simplify to solve for t, that is the terminal velocity, the speed at which the ball drops through the fluid at constant rate. So if we are to find that speed, that which is terminal velocity, simplifying that expression, we are going to have this. So that is Vt is equal to 2g, density of the sphere minus density of the liquid, r cubed over 9 no. R cubed over 9 no. So that is our terminal velocity formula. Our terminal velocity formula. So for those of you that have not subscribed, it is very important to subscribe, because today we had little issues with network. I have to go back and forth, and I cannot be sending the link to Subdin now every now and then. If you have subscribed, the beauty is once the network switched off and I come back again, you will get the prompt, and then you will just click and join. It's important you subscribe for subsequent class. So let's look at some examples before we call it a day. Here we have water circulates through the house in a hot water heating system. If the water is pumped at a speed of 0.50 meter per second through a 4 cm diameter pipe in the basement under a pressure of 3 atmospheres. What will be the flow speed and pressure in a 2 cm, 2.6 cm diameter pipe on the second floor, 5.0 meter above? So the first thing to do is to analyze this question, to know the parameters you are given, and then to also determine what you are asked to find. We are asked to find the speed, and then we are asked to find pressure, speed and pressure. So let's look at the question again. Water circulates through the house in a hot water heating system. If the water is pumped at a speed, so V1 is given to us here as 0.50 meter per second through a 4.0 cm diameter. So we can also find area there to give us A1 V1. Now this is happening in the basement. So since the basement is mentioned, we take that basement as a reference point to be 0 under a pressure of 3.08 atmosphere. So the P1 there is 3.0 atmosphere. What will be the flow speed, that is V2, and pressure P2 in a 2.6 cm diameter pipe on the second floor? So we have diameter 2 that can give us A2, and then we have height, let's say H2, as 5 meters. So the first thing to do here is to find the speed by using continuity equation. So we are going to have A1 V1 is equal to A2 V2. So we can get our A1 because from the diameter given to us here, and we can get our A2 from the diameter given to us here. And then since it's a pipe, we know that A area becomes pi r squared, which is, in terms of diameter, it will be pi d squared over 4. Pi d squared over 4. So we are asked to find V2. So V2 becomes A1 V1 over A2. So that is the formula. So that will help us find our V2. So now, after we've done finding our V2, we now have V1, V2, we have P1, P2. Okay, we have V1, we'll have V1, we'll have V2, then we have H1 is equal to 0, H2 is equal to 5 meters, P1 is given to us at 3 atmosphere, so we have to find P2. So we cannot use Bernoulli's equation to find P2. We cannot use Bernoulli. So the first thing to find the velocity, or the flow speed, we use continuity equation. And then when we've gotten the V2, we'll now use Bernoulli's equation to find pressure 2. So let's move to the solution. So here we have V2 to be 1.182. And then we apply the Bernoulli's equation. Remember that PHY, H1, that is the height one there, is at the basement. So that is 0. So if that is 0, it implies that this term, becomes 0, because the basement is the reference point and is 0. So that term will become 0. Then we make P2, the subject of the formula. So if we substitute and simplify that, we get an answer there, 2.5 atmosphere. 2.5 atmosphere. So okay, let's take the last example for today, and then we'll send the materials so that you can go through the other examples listed there. A pipe of internal diameter 0.04 meter is joined to another pipe of internal diameter 0.0. A pipe of internal diameter 0.04 meters is joined to another pipe of the internal diameter 0.05 meters. If the resultant pipe is horizontal and the rate of flow of water in the pipe is 4 times 10 raised to minus 3 meters cubed per second, find the pressure drop between the two pipes. Now, this pipe is laid horizontal, which implies that even when you apply Bernoulli's principle, the part that has the height will be eliminated. The part that has the height will be eliminated. So let's go on to the solution. So P1 plus half rho V1 square is equal to P2 plus half rho V2 square. Remember I said the part that has rho GH or rho GY will be eliminated because the pipe is laid horizontally. So that becomes 0. So it's as much as solving problem related to Venturi tube. Solving problem related to Venturi tube. So we have to solve for V1 and V2 first, and then substitute, because if you look at the equation, if you look at the question here, we have the internal diameter for 1, internal diameter for 2, and then we have the flow rate. The rate of flow of water in the pipe is 4 times 10 raised to minus 3 meter cube per second. That is flow rate. That is flow rate. And flow rate Q is equal to AV. Flow rate Q is equal to AV. V is velocity, A is area. So now that we have internal diameter, we can find the area using pi r square or pi d square over 4 to find the area of the first pipe and find the area of the second pipe, and now use that to find V1, V2 separately. So Q will be equal to A1 V1. Q is also equal to A2 V2. So we can we'll first solve for A1 and then substitute that into Q is equal to A1 V1 to find V1, and then solve for A2, and then divide Q over A2. That will give us V2. So after we've gotten V2, we can now use this expression to find the pressure. So that is what is done there. A1 plus A1 V1 is equal to A2 V2, and that is equal to 4 times 10 raised to minus 3. So we find A1 first, like I explained, using the internal diameter of pipe 1, and then substitute to get V1, then find A2 using the internal diameter of pipe 2, then substitute to get V2. So after we've gotten V1, V2, we now substitute that value into the Venturi equation. Bernoulli's equation abbreviated for Venturi pipe. So when we substitute down, simplify, we have 2975.4 Pascal. 2975.4 Pascal. So we are going to end the class here today, and then I'll forward the slide to you through the Subdin. Remember to, if you have not subscribed, click the subscribe button so that we'll not be going back and forth, sending link to Subdin all the time. So do that if you have not done that. Very important. You may not get the link next time if you have not subscribed.